So good morning, everyone. Today I'll try to explain a little bit of math behind vision and hearing. We all know that these are the two important ways that we sense the world, and and it's very much rooted in biology. However, what is the mathematics or the algorithmic side of these functions? And that remains a mystery. I mean, it's been studied for many years, but there's still a lot to be discovered. So this is the outline. I'll show, first of all, we'll start with maybe this is a little light. Oh, okay. Can you see the? Yeah, okay. So the visual and the auditory systems are what we're going to discuss. And then we're going to look at it from the linear algebra point of view. In other words, the vectors and all that stuff. And hopefully this will remind you of some math you learned before. And then we'll look at the special class of issue called sparse recovery and how they are applied in imaging. And then we'll switch gear to sound. So it turns out that vision and hearing are related. Of course, they all come from the brain. So this is a picture of our brain, and we observe through our eyes. And then the first stop of visual processing happens in an area called the V1. And this does the observation of, if you look at the image, we decompose into edges, corners. It's kind of like a sketch, right? When you see something complicated, the artist could make a crude sketch. And then you more or less see what is the object. And after that, the signal is transcended to higher levels of visual centers. For example, V2, V4, and even higher. And eventually it goes up to the decision making. So this pathway is what's built in our brain. So with vision, turns out 1/3 of the brain is devoted to processing signals from our eyes. So 33% is very high. And then the whole visual cortex has about 100 billion neurons to process the information. So it's a very large network. And also the speed is 3 gigabytes per second. So it's very fast. Huge supercomputer, right? Okay. So V1 has been studied a lot by biologists. So in 1997, two scientists proposed the following picture. And so here's V1 at the back of our brain. It says that we observe a lot, but somehow God built in more tools for us to observe, decompose the images than we really need. So that's designed by God. And here's the simple picture in 2 dimensions. So this is a very high dimension because the image lives in hundreds dimension. But just by analogy, let's consider the plane. So we have 2 dimensions, so the x, y coordinate. Typically, when we learn in school, we lay down the Cartesian coordinate. So one is here, the other is there. So 2 vectors are enough to represent all the points on the plane, right? So that's the basic. But this design is not just 2 dimensions, it has more. So here's an example of 3 vectors on the plane. So if over here you have 3. And of course 3 is more than enough. But the good thing about 3 is this. If you ever get sick, if you lose one, and there's still 2, so you're still okay, right? So evolution somehow promotes this idea of redundancy. So carry a little bit more than what you need. Because in case of emergency, you have something to go to. If you just carry barely enough, then you'll be in deep trouble if one happens to break down. So that's one. Okay, so with this comes the issue. Then the representation is no longer unique. You can use these 2, you can use the other 2. And of course, you can also use all 3. And the preferred way of representing it is to pick 2, of course. So pick 2 out of the 3, or even pick the least number of 2. So it's like we're going to build a warehouse. The brain is like a warehouse, all kinds of tools. When something breaks at home, you're going to think about 2 or 3 tools that's going to fix the problem. If it's the faucet, you're going to bring a few related to the faucet. If it's the bathtub, you do something different, right? However, you do need a baghouse in the back, a warehouse to support your immediate recovery of, Okay, so in mathematics, we have to design the functions to represent these so-called basis functions, and they're under different names. Gabor, for example, or frames, or things like this. Now, computer can also learn and build the basis functions after seeing millions of images. So, for example, you can get 121. So when you have an image, you decompose it into patches. So decompose into patches of size 21 by 21, so which consists of 441 pixels in there. And after we learn, after the machine have seen many images, they found out the basis functions can be a collection of these guys. And what we see is, indeed, they're the edges, simple shapes. So that means when you have a complicated image, you can write each patch of a complicated image as a linear combination of these guys. So that's the idea. So the redundant basis. Okay, so when you have an image to represent, we're going to pick just a very few out of these 121. We don't need all of them. So it's like a mini warehouse, so just some of them. So how are we going to do this? When something is presented like an image, we're going to pick just a few to represent it. So this is the issue of sparse representation. Okay, so we'll get to it later. Now let's look at the ear. So here's our ear. Ear is connected to the brain, or the auditory cortex. This is actually a picture in the Time magazine many years ago. So, okay. So now the ear has the first stop of the ear is, of course, over here. It's kind of like the analog of V1, right? So you can think of this as the ear 1, E1, and then goes all the way up to the brain. Okay, so if you look at the first stop, it looks like the outer ear, the middle ear, and then goes into the inner ear. And this spiral-shaped the tube is what we call the inner ear. The inner ear is where sound signal processing is done in humans. And if we unwind this spiral into a horizontal tube, and then, like a physicist, we're going to make cross-sections horizontally, vertically, and then we're going to see this. So if you look at the tube in the longitudinal cross-section, it's a chamber filled with fluid. In the middle of the chamber is a membrane called the basilar membrane. When the sound starts to come into our ear, it sends a wave over here, is vibrating. The fluid starts to move in this way, and the membrane starts to deform into a certain interesting shape of this type. It goes like this. So the membrane is like a piano keyboard. Depending on the frequency you send in, the higher frequency ones start to excite the membrane over here. The lower frequency goes more inward into here. So, so this is really like a frequency analyzer. Our ear senses the frequency depending on which part of it gets excited. Then, of course, after the signal is received by the first stop of the ear, it will send it all over to the auditory pathway, similar to the visual pathway. So it will be neural networks, neurons that receive the signal and sends it upward, eventually to form a perception. Okay, so so this is actually one of the basis vectors. It's kind of like representing a vector on the plane with a few vectors. This one, if you discretize it, it becomes a vector. So that's one of the bases for our ear. And of course, there are infinitely many, because you can put many of these guys in here. And also the axis here is length. But it turns out length and frequency has a one-to-one correspondence. Low frequency is mapped over here, high frequency mapped here, low frequency mapped over here. Okay, so you can think of this really as a basis in the frequency domain, because really you're looking at frequency. So this is the frequency domain response of the ear. Now, I don't know if you remember, Fourier transform carries frequency domain to time domain. So if you take a Fourier transform of this shape, then you get the following function. So this is called the gamma tone filter. So you get a trig function over here with the frequency fc, some phase shift, and then there's a decaying envelope, some power in front. And so these functions are used to represent the sound. So when you get a sound signal, it's a time-dependent signal of a certain length, then you project the signal onto these functions. So these functions will be the basis for the ear. And the relation is that if you take a Fourier transform of this function, you get back to the shape I showed you on the last transparency. Okay. So you see that the FC is a continuum variable. So and therefore there are infinite many of these functions, and clearly they're over-complete. They're redundant, more than what you need. Okay, so this is another example of design by God. Everywhere is over-redundant. B is a number. I think it's related to the order. So somehow the shape, it carries some shape information. So if we go back here, I only plotted one. The low frequency ones tend to spread out a little bit more. So the envelope a little wider. The high frequency ones a little sharper. So the B has something to do with the shape. Yeah. Okay. So now let's get back to this issue of sparse representation. We have more than what we need. So if we put the bases into a column, right? If we discretize them into a vector, put them all into columns, then they form a matrix called phi. So we call them the sensing matrix. That's how we sense the signals in the real world. And now we're going to pick a few coefficients out of these to represent the signal that we receive. So the question is, y is given, that's the input. Phi is what we have in our system. And now we want to find the solution x. So this is the math problem. We all know that if m is equal to n, so if this were a square, then it's a standard problem. You take the inverse, right? What we learn in linear algebra. In that case, there's a unique solution. But the non-standard thing about this is that this is a rectangular, what we call a short and fat matrix, right? It goes this way. So, okay. So now you cannot solve it by standard way. Instead, you could use some optimization procedure to solve it. You want something to be sparse, just a few coefficients. What are the quantities that could measure this kind of information? So of course, the straightforward way is what we call the L0 norm. That just counts the number of non-zero components in a vector. If this guy is small, clearly it's sparse. But this quantity is very discrete. It's hard to minimize. Calculus is hard to apply in this case. So the next quantity is L1. This L1 norm is defined as the sum of all the components in absolute value. So that's the L1. Then the next thing is L2, and that's what we are familiar with. That's just the length, the Euclidean length of a vector. Okay. So it turns out that the L0, the counting measure, under some constraint like this, can be relaxed or can be approximated by minimizing the L1 norm, now the L2, and I'll explain to you later. So going this way is called convex relaxation. So this problem tries to approximate that problem. And under certain condition of sparseness of the vector x and certain incoherence condition of phi, there are mathematical theorems that show that you can go backward too. So you can, when you solve this problem, it actually is the L0 problem. Okay. It turns out that the sparse representation arises also in other areas of science, not just vision and hearing, in geoscience, for example. And so there's work back in the 80s involving the L1 norm that promotes sparsity. Theory was done by a group of people at Stanford and more recently in UCLA. So this is really a California problem solved by the Californians. Okay, so that's the thing. And then the practical side is how to design algorithms to calculate the solution related to L1 problem, L1 minimization. And this was again done in California. So this is entirely Californian, you can say. Right? Okay, so now let me spend a minute to explain why L1, not L2. So it's useful to draw the contour lines. So that means you let L2 be 1, 2, 3, and 4, and trace out the shape. The contour lines of L2 are the concentric circles. Contour lines of L1 are the diamonds. Okay, so the difference is these guys have corners, and those guys are smooth. Okay, so when we try to solve the minimization problem, the constraint, let's say in 2 dimensions, will be a line, so it's flat. And when you try to minimize, the problem is you want to find the smallest cone, the smallest level line to touch the constraint, which is the line here. So if you touch it with a circle, because it's smooth, typically you will touch somewhere in the first quadrant in this picture. So and strictly inside, and therefore it's not sparse because both components are positive. But if you touch it with a diamond, and then the corner will touch the line first, and therefore it's more likely that you get a sparse solution on the axis, so either here or here, right? So that picture explains having corners is an advantage when you look for sparse solutions. Okay, so this is the picture in the plane, and you can also go to the 3 dimension in space, so then you get a polyhedron here, and then a plane here. And when they touch, more likely you're going to touch it with the corner or sometime maybe the edge, but very unlikely you're going to touch it with the facet with lower probability. Okay, so this is the idea. Now let me explain some algebra behind the issue. So when you try to solve it, typically we're going to do it in the unconstrained form. So that means the linear algebra equation is put into the first term here, the phi x minus y. We want it to be as small as possible. And then we regularize it by adding a penalty, so that's the L1. So to solve this problem. And the difficulty is that the x is a vector, and different components are coupled because of the phi. Okay, so the idea is, can we solve it by decoupling it, right? So therefore, let's look at in 1 dimension what happens. In 1 dimension, so the first term is called the fidelity term, or the data term, and the second term is the L1. So in this case, just 1 component. So this problem, even though this is absolute value, it's not continuously differentiable, but you can break it into positive x and negative x, and then use calculus, differentiate it, find the solution. So this could be a problem in calculus 1, after you learn differentiation. And then you can find the solution, and the solution is given by this function. So it has an exact solution. So the solution is the following. You take the absolute value of the data, you shrink it by an amount lambda. And if after shrinking it becomes a negative number, you just take it 0. So this is the max. It's called the shrink. Okay, so now what happens if you go to the several dimension? If x is a vector, now the component, if it's in this form, it's no big deal because when you write it into a sum, each component can be solved independently like this. And therefore, the vector case is same as the single variable case. So, therefore, the answer is a shrink component by component. So therefore, this function also provides a solution to the vector case if x is decoupled. Okay, now come to the coupled case. So the idea is we want to decouple it. So let's write x to z, and then add a constraint x minus z equal to 0. Of course, this is going to be exactly the same as this. It's just a change of name, right, from John to Steve. But otherwise, it's the same. OK, but then we treat it as a constraint problem. And French mathematician Lagrange said, you can introduce a multiplier called P, so the Lagrange multiplier, and put the constraint in there to remove the constraint, and then you minimize. So now the x and y looks separate. So OK, so then the idea is, let's first minimize over x. So now you minimize over x. The z is independent. You don't worry about this. And then this is x here. And I put in x minus z squared as a penalty with a parameter so that x and z are not too far off. Because if they deviate, then there's a penalty here. Because we want x and z to be close. OK, so and now you look at this, it becomes a standard quadratic function. Because x, you square is a quadratic. This is linear. This is quadratic. Quadratic functions are smooth. No problem with minimization. And that's the least square, essentially. So the first step is to minimize over x. Fix the other variables, z and the p. Second, after you get the x, you minimize over z, so alternating. And now when you minimize over z, look at the z only appears here, and z appears here. That's exactly the problem we solved on the last transparency with decoupled components. So therefore, the solution is the shrink, right? If you split into z, then it's the shrink solution. OK, so each step has a well-defined solution, and then at the end, you update the multiplier. So by this way. OK, so that's the, to summarize, what we do is we split and we shrink. So only two things you do. The Californians like something quick. So this is how we solve them. OK, so this is L1. But now you ask the question, can you do better than L1 if you relax the convexity? OK, so then people say, well, let's try something like a half. So you mimic the L1, you replace the 1 by a half, and then you define something called a half norm. Also, more recently in Irvine, we try something like L1 minus L2. So this is also a non-convex property. Why these quantities? So let me show you. If we draw the level lines again, then the L1 half will look like this. Remember, the L1 is a diamond, but the L1 half has cusp in here. So if you want the corners to do the wonders, the cusps should be sharper, like a knife. It should cut the plane, do the sparsity job even better. So that's intuitively the reason. And if we plot the level lines of L1 minus half, you see that they have some similarity over here. OK. So that's the, properties of L1 minus 1 half is the following. First, it's still a Lipschitz function. In other words, the derivatives will be bounded, whereas L1 half, when you take a derivative, is infinite at 0. So the L1 half is what we call the Holder continuous function. The L1 minus L2 is still Lipschitz. And the other beautiful quantity property is that L1 minus 1 half, L1 minus L2 is always non-negative. So this follows from the elementary inequalities. And it is equal to 0 if and only if x is 0 by itself or f is 1 sparse. So it's very sharp. If it's 1 sparse, then think of this as energy. Then the ground state energy corresponds to 1 sparse solution. The other thing is, even though it's non-convex, but you can write it into a difference of two convex functions as a special form of non-convex. And then lastly, it's made in UCI. So for that, we'll go with it. Yeah, right. OK, so now we're going to solve this non-convex problem. We know how to do this now. Now let me add the minus L2. So what we do is we're going to linearize this quantity at each step. So suppose we start at 0. At the first step, we just drop that term, so it's L1. So we start with the L1. And then after you iterate, solution becomes xn. And then you linearize that term and put it here. Okay, so and then you solve the subproblem. But in the subproblem, only L1 appears, so it's the same problem we discussed before. It's just one more layer of iteration, and then you can do it. So the algebra also goes through like before. Okay, so let's perform some tests, compare them, see what happens. So one measure of the coherence of a matrix is this quantity mu, and that's the maximum of cosine of the angles of all pairs of columns. So what it does is to measure how parallel the columns are. If the columns tend to go like this and this, not aligning with one another, we call it incoherent. It's like you drop a hairpin on the floor at different times, they point to different directions. But if you tend to align, then it's a coherent matrix. Okay, so there are two regimes. One is mu is small, so that's called the incoherent or well-conditioned. In this case, the columns point in different directions. The other one is ill-conditioned and coherent, and that's when mu is close to 1. That's when all the columns start to align. So here's a specific matrix, cosine of 2 pi. So at J column, we define it as cosine of this c is a vector with random components uniformly independently sampled on the interval 0 to 1. And then we're going to divide it by a factor f. If f is 1, then mu is small. When f becomes larger, this mu will go up to 1. For example, at f equal to 10, it's already 0.99. And when you go up further, it's even more. So this example gave us a way to control the matrix and its coherence properties. Okay, so here's the comparison. The blue is L1, so it's here. And the red is L1 half. And indeed, L1 half does much better than L1 in the incoherent case, f equal to 1. And the black is L1 minus 2, our penalty. However, as you increase the coherence, you see something interesting happens, that the red start to fall behind. The other two guys start to take the lead. Okay, and as you increase f further, then this pattern continues. In other words, L1 and L1 minus 1. So L1 minus L2 always improves on L1 consistently. In particular, it's one of the best if the coherence is high. So, so if the matrices are incoherent, then the half is the champion, the individual event champion. And if the coherence is high, then the L1 minus L2 is the champion. So the UCI guy wins in one event, right? Okay, so that's the picture. So let's try to apply this L1 minus 1 half to some problem. So this is a hyperspectral imagery problem. You take a ground picture from the air. So this camera has hundreds of channels. Our Euro camera has only 3 channels, RGB, but this one has higher spectral resolution. The reason is that it tries to sense the materials on the ground. For example, here you have grass, here you have trees, and different objects on the ground has different shape. If you look at the response across all the channels. This is why you need so many channels. So if I plot it across the channels, for example, if the tree will correspond to this red curve. So that's the typical response from a tree. And then if you look at road, for example, here's the road, road here. The road will correspond to the blue. And then the building and rooftops, dirt, and they all have their own signatures. So these are the basis functions, kind of like the image basis functions or the sound basis functions. So these are the signatures correspond to these materials on the ground. Okay, so the mathematical problem is the same. Given the input y, given the signatures, we put them in the matrix phi, then we try to find the x. In this case, x corresponds to the concentration at one spot, at any spot of certain material. So, okay, so the next slide, we plot these 6 materials sensed by, solved by L1, which is over here, and L1 minus L2, which is over here. And the difference is that the sparsity look approximately the same. However, the L1 minus L2 tend to give sharper solutions. So these concentrations are color-coded. If they're very high, it's 1. If they're low, it's 0. So in the L1 case, we get color like green and yellowish. So for example, it's about 0.67. But if you're the same spot over here, it's close to 1. So that means this quantity is more sensitive. For example, in this case, it's probably the grass, and in this case, the tree. So you will get a sharper resolution of the area in terms of the materials. You can see the materials better from these plots than that one. Okay, so that's one advantage. And the other one is something called array imaging. So this is where you have some objects hanging over here, and then you send light, shine it through the objects. They get reflected and get received. So over here you get sensors, and they send out light and receive the reflected light. In the problem we are looking at, we only receive the amplitude of the reflected light, not the phase, because phase information is hard, direction information is hard to get. Okay, so the problem is like this now. So a matrix A times the unknown x, the unknown r, we only get the magnitude, or the square, equal to b. And we know r is non-negative. The question is to recover the r. Okay, at first sight, it looks very different from the linear problem we had before. However, it's a quadratic function. If we define the matrix r dot to r transpose, this will be a rank 1 matrix, and therefore a singular value, or in this case, the eigenvalue would be 1 sparse. In other words, only one non-zero eigenvalue, the rest of them are 0. And if you define x this way, this quadratic equation can be turned into a linear equation with some linear operator a in front, so constrained like this. So now it starts to look like the problem we had before. If we do L1, then we minimize over sum of the eigenvalues, so that's the trace. And if we do the L1 minus L2, then there's a trace minus the sum of square of x. So that's the Frobenius norm. Okay, so here's the comparison. So with 4 objects over here, you shine light 10 times. With L1, you can still hardly see the location of the objects. But with only 3 illumination, you shine light 3 times. With L1 minus L2, you can get pretty good location information already. So this helps us visualize the objects. Okay. Okay, so this shows the advantage of this non-convex penalty. And so the next question is there a penalty that is less sensitive to mu, right? So we have 2 individual events. One is mu small, the other is mu large. Somebody is good at mu small, somebody is good at mu large. But is there somebody that's always good across mu? So we play with that. We find out that there is indeed such a penalty. It's called the transformed L1. So L1 is the sum of the absolute value of the components. So if we use a nonlinear function to transform it and then sum up, that's called the transformed L1. This nonlinear function is just a ratio or a bilinear transform. A is a parameter, t is the variable. So this is the ratio here. Okay, so if we plot the level lines, then when A is large, like 100, you start to see the diamonds. So in other words, it can recover the L1. When A is 1, it looks like the cusp. So it's kind of like the L1 half. And when A is 0.01, very small, the level lines tend to cluster around the axis, kind of like L0. So this guy can sweep out all the penalties we discussed so far. Okay. And if we do a same test, we find out the following, that here's the L1, this color over here, and this is L1 minus L2, this is L1 half, and the TL1 is here. You see that as you increase F from 2, 4, 6 to 8, the red curve, this one is at the top, this one is the top, this one is the top, and only at the very end, F equal to 10, it becomes second. Of course, our first L1 minus 1 half, the green, overtakes at this point out. So, so this is actually a very robust quantity. So it's an all-around champion. It cannot win every event, but overall it's very good. So this is, again, to summarize, it can be expressed as a difference of convex functions again, and the very same problem, the one-dimensional problem, but now with L1 replaced by this transform L1, can also be solved in closed analytical form. So there's some math to do, but you can do it. And turns out you get the shrink function, a new shrink, a UCI shrink, come out of this function. Of course, it's made here. So, okay. So now let's summarize on the shrink, the California shrinks. The soft shrink is here. So that was discovered already in the late 80s and the 90s. So here's the soft shrink function we discussed before. At a certain level is 0, beyond which is a linear function, so soft shrink. The half shrink is like this, has a jump, discontinuity, and here is a more complicated function. It looks straight, but it's actually a little curved over here. And our TL1 has two regimes. One is what we call the subcritical. This is when A is large, so it's closer to L1. What you get is a shrink that is continuous, like the soft shrink, right? There's no jump, but over here there's a non-linear curve instead of the straight linear curve. And then when A is small, it's the other regime where you get the supercritical shrink, and they have jumps, like the L1 half. So those are the two that we discovered more recently. And okay, so we're very happy about that. So that's the summary of the sparse recovery problem. And let's move on to sound. So, so the best mammals that rely on sound for their life are the bats, because they cannot see anything. And we know that they're so good at finding the objects and stuff. So it turns out the bats use two ears, the left and right. And then when they send out the echo, the left signal and the right signal all come into their brain, and they compare something called the interaural time and intensity differences. So in other words, they compare the intensity of sound they receive from the left ear to the right ear. Also the time delay, right? Which one comes first? If my right ear receives signal first, that means the object is more likely on my right side than on the left side. So something like this. Okay. So when we try to solve this sound problem, so we always have this experience that when you try to make a phone call, then there's a jackhammer somebody is operating. It's hard to hear. And if you're making a phone call in a restaurant when lots of noise, and it's hard for the other recipient to hear your speech. So it would be nice if we could separate them by using the two ears. So by following a similar principle as the bats, as far as we know. Okay, so the sound problem, so now a little bit even more math, is this. That remember the signal, now I changed notation slightly. So here's the received signal, and here's the source. And from the source to the received signal in your ear, it goes through an environment. Environment is like a matrix. However, here there will be delay, because after I send the signal out, some of the signal goes straight to your ear, some gets bounced to the wall, and then gets reflected to your ear. So if you sum up all the components, this will be in terms of P, it turns into this form, P, K minus P. This is called convolution, right? So if there's no delay, if capital P is 0, only one term over here, then we're back to the last problem, right? So then it's just a matrix. So in this case, there's more. There's also a convolution involved. So this Aij, this coefficients, is related to the room. So this is called the room impulse response. If you plot it as a function of p, it looks very complicated, something like this. So this is the signal you will receive if someone fires a shotgun at a location, and you receive a signal like this. So each 100-meter race athlete, when the shotgun starts in their ear, they receive something like this. The first signal is very high because you get the direct rival from the source. So there's a peak. And then there will be other reflected signals coming into the ear. Eventually, they become very, very tiny, but they're still coming. So in a room of a typical size room, office size, takes about 750 milliseconds for this signal to die out. Okay, so that's the Aij in the model. Okay, so I'd like to show you a good math trick. So suppose we have two ears. So that's x1 is equal to, so I use a star as a shorthand for the convolution. So this H11 convolve with that. So you get these 2x2 system with convolution over here. So what we do is, let's suppose S2 is the foreground, S1 is the background. So we're going to separate the foreground from the background. Suppose the foreground is a speech. So when we talk, we make pauses, not continuous. Occasionally make pauses. During a pause period, the S2 will be 0. Okay, so then there's only two terms over here. So if we multiply the first equation by H21, second equation by H11, we subtract, then we get 0, right? So they cancel out. Okay, so that means during the pause period, this equation is approximately true. So therefore, we formulate an optimization problem like before. So this is the fidelity term. We try to minimize and then find short solutions because we mainly want the first few peaks, not the entire thing, and use L1 to penalize it. And solve this problem, get the H21, H11, and then during the on time, the same linear combination will give us this following expression, which is S2, the foreground, up to a convolution. Even though we don't know this entirely, but the human ear is not very sensitive to S2 or a convoluted S2. In terms of understanding, there's not much difference. So you can consider this problem essentially solved if you're able to get H21 and H11. So those are used as the filters to get solution. Okay, so how do you get the pause, right? So, so here we're going to follow the Bat's idea. So look at the time frequency domain and look at the, on the log scale, the amplitude and the phase, the difference. So here's the phase, here's the amplitude, so in log scale. And if you put your data points all in there, so we're going to take Fourier transform, get all the frequency and time points on the data. And what you see is they form two clusters, 1 and 2. And that shows you there are two sources in the signal. And so this idea roughly separates the two sources already and help you to find the pause. Okay, so that's kind of the Bat's. In the Bat's brain, when there are two objects located at different locations, you could actually sense them by you using the amplitude and phase difference. Okay, so I'm going to play you some signals. And let's see. So here's the first one. Okay, so the second signal will be similar.
Find Italian restaurants in Irvine, California.
Okay, so now enhance it.
Find Italian restaurants in Irvine, California.
Okay, so that's the one recording. And the second one, perhaps even, okay, so let's play this here. Okay, then enhance. I don't know if you hear anything other than the sound, almost nothing. I was reading an article where the sound was playing, the music was playing. Yeah, so here's the enhanced. So this is not bad. Of course, we use a high-end microphone, Kinect mic array. I mean, it also help a little bit. Okay, so now it's time. So I've done a little bit math. I hope it's okay. And now let's go on to higher levels. Remember at the beginning, we talked about the V1, but there's more beyond that. So it turns out that in recent years, Google, Microsoft, they're starting a whole line of research on finding further features. For example, we discussed the 121 features at the lower level, the first layer, what do they call it? And then you can use something called the deep neural network to extract more features in the second layer, third layer, and so forth, for things like face identification and stuff like that. So there's more layer to do. And for speech recognition, something very similar is happening. So like Siri, the system will follow more or less this following structure. So we receive sound, in waveform like this, and then we do our projection onto the basis functions, get the raw features or the first layer features, so auditory filter coefficients. So this is a picture of a spectrogram showing you over here is time, and this is frequency. Anytime you have a certain concentration in this plot, it shows you that, for example, here the concentration energy is in higher frequency. It's more like a consonant. And over here you get low frequency energy, more like a vowel. And then so consonant to vowel to consonant. And then this is another vowel, a little longer than this. And this is another consonant. So that's the raw feature, the first layer feature. And then you can go into neural network to model something beyond these low-level features. They're called word model. And these are humongous animals with millions of parameters. You have to train them on speech corpus for some time on big machines. And then after that, you get the parameter set. And then when new signals come in, you're able to run the model with the trained parameters to compute the conditional probability that you try to calculate the probability given the word J, which is the highest J, so that the observation gives you the higher probability. So through this, we are able to match a word with the observation with the word. And then you have to also use some language model and something more related to that, and eventually you get a text. So from speech to text. Okay, and this at this point, because this part is very heavy, so you can only do it in the cloud. If you lose internet connection, it doesn't work. Okay, so there's still work to do to make this part simple, so that even when you're in the forest, out of touch, you can still make the mapping. Okay, so to conclude, we have shown some good math that allow us to understand and compute something called sparse representation, signal recovery in images and sounds, and there's a lot more work to be done. So I'd like to thank my team, postdocs, graduate students, collaborators, and very fortunate to have centers and programs at UCI that relate to various aspects of sounds and images, and my colleagues in math, chemistry. I work with some people in chemistry. Didn't have time to talk about that part today, and so I'll stop here. Thank you very much.